Hi, and welcome back to the data science course. Continuing with the regression lecture series. In this lecture, we learn about random forest regression. So we've already explained to you what decision trees are and what ensemble algorithms are. So now we'll see how they are used to build random forest regression models. So a random forest regression model is an ensemble of decision tree estimators, and it trains multiple such estimators in parallel on subsets of the data set that has been given, averages their predictions, and then reduces the errors to give you the best results. Now, how is this random sampling done? We use something called as bootstrap sampling. This has already been explained in the sampling lecture. So just to repeat, in this random forest model, you are creating subsets of the data set which has been given to you, and each subset is chosen at random with replacement. So when you select certain values in a subset, they are replaced back into the original sample before the next subset is selected. So that way, your random sampling ensures that it covers the entire data set for each subset selection. And of course, there could be certain repetitions. But that's what you want to see, how the model behaves with different variations of the sample in each tree. So here the distinction is the training set is for 1 to n values, and your decision trees are from 1 to m, and m is less than n because you've separated the training data into M subsets, which are then used to build M decision trees. And each subset sample runs from 1 to A, where A is less than N, right? Each sample subset will be less than the total training data set that has been given to us. So it will run from 1 to some variable A. And similarly, all the other samples would be of the same size, but will be subsets of the total training data. So, just to repeat again, that we've already explained decision trees and ensembles. So you know how these trees are built, how the nodes are created, how they are split into branches, how the child nodes are determined, how the leaf nodes are determined, what are the different metrics used. So we've covered that. So now using all that learning, all we have to do is now formulate the random forest model, which creates multiple trees and takes the average of the predictions. So what you've got here is a model y, which is a function of the independent variables x, which again minimizes the information gain, optimizes genuine purity to 1, and minimizes the errors. So it uses mean squared error. So you still want to minimize the difference between the actual and predicted y values, but at the same time optimizing the metrics of decision trees. So we know y is the dependent variable, x1 to n are the independent variables. What we are doing now is taking the average of all the predictions yi had. So each decision tree gives an estimate of y values. You do that for all the decision trees, then you sum them up, take the average, and that gives you your y hat, which is the estimated values for y. Note that this output y hat is a real number, right? We are predicting values on a continuous scale uh, because it's a regression model and the bond prices are on a continuous scale. Uh, but you could apply the same thing to classification, which we'll cover in the classification lecture series, which gives discrete outputs. Now, how do you introduce randomness into this model? This model is called random forest for a reason, right? You're sampling the data to create subsets by doing random sampling. Now, that is ensuring that your model is able to learn from different variations of the data. And now what we want to see is how this randomness is introduced into the model. So you do that by the sampling technique. That's the first thing. And the second thing is by varying the parameters of the model. So we've shown you in different algorithms up till now in regression that all of their definitions have certain parameters which you can define, vary them within their ranges, and they impact the output values. This will of course be covered in the grid search CV lecture where we show you how to optimize these parameters. But what we're trying to say here is that combined with the random sampling, the variation of parameters like the number of features used for splitting the node, the number of samples you want in the leaf nodes, the tree depth you want to go to, they ensure the model is tested for multiple variations of the data, thereby creating a random forest model. And the benefit of doing this is that it reduces the variation of the results that are generated by the estimator because you've used multiple variations of the data on the same estimator and you've averaged the results. Now, what we'll do is look at an example of what a random forest model looks like visually, and then we'll show you the Python code for building a random forest model. And of course, we'll be using scikit-learn's grid search CV k-fold cross-validation in a later chapter to optimize the parameters. So let's look at a random forest example visually. So if you remember, you had a decision tree which had a root node at the top, and then you had child nodes which had leaf nodes. So now imagine you had multiple such decision trees, and each tree had a sample which runs from 1 to A or 1 to B and so forth. And each of these samples is a randomly chosen subset of the training data set. So you keep splitting it into different smaller samples. You use it for each tree, which then gives its prediction for Y, the Y hat. So you have one Y hat output set here, then you have another set of Y hat outputs here, and you get them till all the M decision trees. And then what you have to do is take all the Y hat values and average them out. So generally the benefit of averaging, if you remember, we've discussed this in statistics, that it tends to reduce the variance. And this is a concept used in different machine learning models and general statistical systems too. Okay, so now that we understand how these random forest regression models are built, let's look at the Python code, how they are built. And before that, let's show you the scikit-learn guide for the random forest regressor. And you can see in the class definition, there are so many different parameters that you can specify. You can optimize these. Number of estimators is effectively the number of trees you want to build for giving the outputs. The default is 100. You can try for higher trees. Just remember, the more the number of trees you have in the model, that many number of parallel calculations will be performed, so the longer it will take. So you have to optimize which is the best number of trees to get the ideal results. Then you can define what kind of error metrics you want to use, the depth of the tree, the split node criteria, the minimum number of samples to create the leaf nodes, then what are the maximum number of features you want to use. Generally, you want to use a subset of the features, or you could use all, but that would make the tree very complex and expensive to process, because if you're using all the features at each node, even though you're building these multiple decision trees in parallel, you'd still need a lot of processing resources to build the tree. There are some predefined methods to select the number of features, or you could specify a numeric value, and of course, less than or equal to the number of features. And then you can see there are some other parameters which you can specify. Number of jobs is used to enable parallel processing, provided your local machine or the cloud platform has that ability. And then one of the things you'll see with these tree-based models is they allow you to see the feature importance, and then that enables feature selection. So this is a very good feature for tree-based models like Random Forest and XGBoost. So we'll show you how to use that to further improve the model. Okay, so now let's get back here. So we've explained what some of these parameters are and what is the default value and how to select them. And then later on, when we do grid search CV, we'll show you how to optimize these parameters. We've mentioned that the random forest model is good for interpretation, and it's because of the feature importances attribute. So what happens is that the model calculates the relative importance of each feature or independent variable x. They have values between 0 and 1, and then they all total up to 1. So what it does is allows you to do feature selection. So there might be certain x values or features which are more important than some, and they will most likely have higher feature importance value, whereas the less important ones will have a lower value, and you can most likely drop them and rebuild the model without these x variables or features, because they are just not relevant for building the model. And there's good possibility you will see the model improve in terms of its output predictions. So now let's look at the Python code to understand this better. So here we are. And again, we start by importing the libraries. So you see the normal ones, pandas, numpy, model selection metrics. But for the uh, model class library, we are using the sklearn's ensemble module. And within that, we're using the RandomForest regressor library. And again, you see we are using the same template and following the same process of building the machine learning model. You're importing the data, same location on GitHub. You can go back there and check it. The data file is there. Similarly, this code file is under the regression chapter in examples. You split the data into independent and dependent variables, reshape the variables as required, take out the validation data set, remove it from the sample data. On the remaining sample data, you apply the train test split function to split the sample data into training and test sets. You can vary the split size, so you can specify 25%, 30, 40, whichever works. So you can try all these different variations. And then we create the random forest regressor object, which is the estimator. So you use the class, pass it some default parameter values. Now these are based on the default settings in the model definition, and some based on experience. And of course, we'll learn how to optimize them. So once you've created the estimator, which is the random forest regressor, you can now fit the training data to it. Once you've fit and trained the model, which is the estimator, you can now predict the y values using the x test data. So once you've done that, you calculate the error metrics, plot the y actual and prediction values to see visually how they track each other. And then comes the feature importances code. So what you can see here is once you've trained and predicted your data using the estimator, you can now see what the importance of each feature is. And that is effectively a set of numeric values. So we can plot it visually and see which is the most important feature or set of features. And finally, you validate the results with a independent validation data set, which we remove from the sample data. So let's run this piece of code step by step just to get a good idea of some of these new features in random forest regression. So we'll run this whole part of importing the data, splitting it, and creating the validation data set, and then creating the training and test splits. So if you run that, you've now got your data. So if you look at your original data set, it's the same macroeconomic data. So you've got all the US macroeconomic data for a number of years from 1999 to 2019. And we've also got the bond price and yield for US 10-year government bonds. So same data. And then you've got the training and test set. So if I look at the training X set, that's your X variables. If you look at the Y train, your bond prices, and similarly the rest of the data. So now let's create the estimator for this random forest regressor with the defined parameters. We'll do that. And then let's fit the data. So now your model has been trained, and now let's predict the Y values using the X test data. Great. So now we've got the Y pred values. So, they're all predicted bond prices. Let's calculate the errors and print them. Great. And now just look at the results. They are very good. Look at the RMSE. It's 2.37, the lowest we've seen amongst all the models we've tried up till now. And the R square is 0.93. It's pretty close to 1. So what we've seen by using all the different models on the same data set is that we've progressively improved the results, showing the importance of the data science process of selecting the right model for the problem that you have and given the data set size. And we've seen that in this case, it's a multiple linear problem. But do we want to use a simple multiple linear regression model, or do we want to use the non-linear tree-based models? And we've seen that the tree-based models are giving us far better results, and that is something you'll see quite often in the regression models. You'll find that random forest, XGBoost, and other ensemble tree-based models are far superior to the simpler linear regression models. And we've explained the reasons for it. They have conditional logic. They use different features in different combinations, and they follow the human decision-making process, which makes them easy to interpret. So there are various benefits to using random forest regression models. So let's just plot the predicted and actual values for y and see how well they track each other. And you can see, wow, I mean, they're practically tracking each other so closely, except for this one spike. Everything else is very close. Um, so now let's look at the more useful aspect of random forest regression models, which is the feature importances array. It's a numeric array for each x independent variable. And what we can do is plot it because seeing it visually makes it easier to understand. So we'll run this piece of code there. And now you can see each x independent variable and its feature importance value. And you can see that the interest rates have the highest value, making them the most important variable for determining the bond prices. And that actually makes sense because if you remember, we'd explained for this example that bond prices are calculated using interest rates or the yield, and the yield is inversely related to the bond prices, and yield being directly related to the interest rate. So we have a relationship here between bond prices and interest rates, uh, even though it's inverse. So what we see here that even the model has picked up on that criteria. And then there's the unemployment rate, which is probably a small value, but still significant enough. But if you see some of the other features, they are very low values, so almost insignificant. So you could actually drop them and replay the model with just two or three of these features and see what the results are. If it improves the model, that's very good because then you reduce the amount of processing resources you require to build the model. So if you look at the feature importance array, you'll see you have these numeric values. So it's quite useful and it's something you won't see in say a simple multiple linear regression model. Okay, and finally we'll do the validation test. So if you run that, again you see the difference between the predicted and the actual value for the validation data set is minus 1.26%. This is again the lowest we've seen in all the models. So if you remember, even in the decision trees, it was around minus 2.5, and the RMSE was also high. So you can see that the random forest model has improved on the decision tree model. And we explained that, right? Because what you've done is you've used multiple decision trees and then averaged the results, which is a useful and widely used statistical concept across machine learning and different fields, right? So the benefit of averaging quite often is it reduces the variance, removes all the unnecessary noise, and that's the benefit you're seeing here. Just one thing I'd like to mention that this improvement you've seen in random forest over decision trees is something you'll see across different aspects in machine learning. What happens is that as research improves, new models keep getting released, and there are either improvements of older models or brand new models. But the benefit of learning all these basic foundational models is that as these new models or improvements are released, you can easily learn them and use them and understand why they are better. So that's why we've taken this entire step-by-step approach of using all the base models to explain the same example so that you can see the variational improvement in the results. Okay, so as you can see, we've given the uh, summary of that result here, and you might see a slight difference again in the RMSE and the validation difference values, and that's because of the Python code being run in the live environment. And whenever you do that, you will always see slightly different results, and that's because you're doing random sampling of the sample data, which will of course give slightly different results. You can stabilize this result set using algorithms like grid search CV, which we'll show you in the next couple of lectures. Okay, so with that, we'd like to end this random forest regression lecture, and I hope that by now you've seen the benefits of using different regression models, the benefits of decision trees, ensembles, how to build the machine learning models using different libraries, how to code them, how to visualize the results using the libraries, and other manipulations. And our expectation is that now you're well versed in building machine learning models for different regression problems. So with that, we'll end this lecture on random forest regression. And in the next lecture, we'll discuss XGBoost. Thank you.